Welcome to our continuing study of Newton's laws. Today we're going to take a closer look at friction. Up to this point you've probably done a variety of problems already in a variety of scenarios, multi-body problems, objects on a pendulum, Atwood machine, modified Atwood machine, but we've been looking at those in the absence of friction. Now we're going to add friction in and see how those various scenarios change. Basically we're going to go back and resolve all those problems but adding friction in. But before we can do so, we need to have a basic grasp of the force of friction and what affects it, and then how it's going to affect our motion that we study. Let's get started. Friction is a force between two solid surfaces that acts parallel to the surfaces. So in the image on the screen, you see a man pushing to the right, and you see the friction force opposing to the left. And then you see a microscopic zoom in right here, okay, and that gives you a little bit of idea about the source of the friction force, okay. Now let's look on the screen. You see that basically when we zoom in, even smooth surfaces are rough at the microscopic level, right? So one of the reasons that there's friction is that those surfaces, even though they seem smooth to the touch, are actually pretty rough. And the hills and valleys, those microscopic hills and valleys, they interfere with each other. All right. Another thing that's going on at that level is that there's some transient bonding that's occurring. Okay, some electromagnetic interaction, right? Likes repel, opposites attract. So that's the reason for the friction force at the microscopic level. It's actually incompletely understood at this point. Okay, it's actually fairly complex, but we found some basic ways to simplify it, and that's because of the following. If you look at the other part of the screen here, okay, it turns out that despite the complicated nature of the friction force and all the things that are interacting to cause it, it turns out that over a pretty wide range of speeds, okay, the friction force is constant. In other words, it's not velocity dependent. That's going to vastly simplify the equation that we use to model the friction force. All right, as you probably can surmise, the nature of the surfaces is going to play a big role in how much friction there is, right? A rough surface is going to have more friction, right, like sandpaper versus, say, a piece of glass. Okay, so we need another measurement here that's basically going to measure the roughness of the surfaces compared to each other. And obviously, when we do this comparison, we're going to need to know which two surfaces we're talking about, right? We can't just talk about one surface, because it's all about how the one surface interacts with another. So we have this saying that we've come up with called the coefficient of friction. Okay, it's the Greek letter mu, which is like a backwards y almost. The Greek letter mu. Okay, and that's the coefficient of friction, and it's defined as the following. Okay, it's defined as the ratio of the friction force to the normal force. Okay, and it turns out that that's going to be different for different surfaces. All right, the rougher the surface, the bigger the coefficient. Right, the rougher the surface, the more friction there will be, and the bigger this coefficient will be. All right, now notice I can solve for friction here. Okay, I can just multiply both sides by n, and I get this. I get an expression for the friction force that's dependent basically only on this normal force, okay, and this coefficient of friction, which will basically tell us about the relative roughness of the surfaces. On the screen, you see an example of how friction can be manipulated by the value of the normal force. So I'm going to write our expression for friction again. Okay, you can see here that the higher the normal force, the higher the friction. Basically what's happening is, in this example here, right, by pushing downward and horizontally, what that kid is doing is basically making those surfaces, the microscopic hills and valleys of the surfaces, press more into each other, causing more interference, therefore more friction. Okay, whereas in the example on the right, by pulling upward, he's allowing those surfaces to be a little bit less pressed together, reducing the friction. All right, on the next screen you see another aspect of the friction force. We like to call the friction force a lazy force. Okay, let's see why that might be. If you look at this example here, and you'll notice this with any object, right? If you're not pushing on an object, there's going to be no friction, right? So since you're not pushing against it, friction's not going to push against you. But when you start to pull, like when we start to pull on this block here, okay, so let me pick a color. Or when we start to pull on this block here, there's going to be a little bit of friction force, okay? If I pull harder, there's going to be more friction force. But in each case, the block has yet to move. But at some point, I will begin to pull hard enough so that I overcome the maximum amount of friction that these two surfaces can offer against me. Okay, but notice how the friction force grows before reaching a maximum. Another thing to recognize is that friction force is going to be independent for a given object how much surface area is touching it. You might think that there's more friction here because there's more scraping, but because the weight is spread out over a greater area, the surface, even though there's more surface to scrape, the surfaces aren't as pressed into each other, right? The pressure is less. So that's why it turns out it doesn't matter how you orient this block, the friction force is going to be the same. All right, let's go to the next screen. You'll see another aspect of friction, which is that friction actually comes in three varieties. It comes in kinetic, static, and rolling. But we're not really going to consider rolling friction. It turns out rolling friction is much less than static and kinetic, and obviously, as the name implies, comes into play only when we have one surface rolling over another. We're going to focus on static and kinetic. And what you see here is you see a graph of applied force, and you see how the static friction grows, right? This is the lazy aspect, okay? The more you push, the more it pushes back. And then we hit that maximum point here, right? And then what happens is you see a drop. And if you ever moved a heavy piece of furniture, you've seen this happen in everyday experience. You push on that fridge, right? You push, push, push. And when it finally gives, then all of a sudden it's a lot easier to keep it moving, right? And that's because you've transitioned from one kind of friction, static friction, to another type of friction, kinetic friction. And one way to think about that is that once you get those surfaces moving, the bonding that occurs, right? We talked about the bonding earlier, the transient electromagnetic bonding. That's not going to be as evident right now. The only thing that's really happening with friction is that those microscopic hills and valleys are catching. So once you get those surfaces to move against each other, the electromagnetic bonding has less of an effect, and so you have less friction overall. So we have a couple ways we can write that. Okay, we have basically. Let me write static friction first. Okay, so static friction can be written this way, less than or equal to. Okay, so we have one value for a static situation, and then for kinetic friction, we have this situation here. Okay, so you see that we have actually two types of mu, one for the static situation and one for the kinetic situation. And that's actually summed up on the next page here. I have a table of mu values. Okay, let's take a look at that. And you can see that it depends on which two surfaces, like I mentioned earlier, are interacting. And you notice here in every case that this value is static friction, right? All these values are higher than kinetic. Notice also that a value of 1.0 is very high, right? That means the ratio of friction force to normal force is 1. Remember, the way that we got mu here in the first place is ratio of friction force to normal force, right? So a ratio of 1 means like there's as much friction as the weight of the object. That's huge. Okay. We've actually used this example to save lives, okay, in our society by, and I'm going to give you this example here, okay, of guardrails versus concrete barriers. When we first built barriers on roads to make them safer, we used guardrails, right? Those metal rails that run about maybe knee or hip high, right? But if you think about that, when a car runs against it, okay, what they found is that's basically like steel on steel, okay? Let's look at the steel on steel kinetic friction, right, 0.57. So if you have your car, right, basically steel hitting steel, you're going to get some friction as those two metal surfaces scrape. But what we have nowadays, okay, is we have what you're seeing a lot more is you're seeing these guardrails being replaced by, if you look on the side of the roads now, you'll see these concrete barriers that are shaped like this. Okay, so it's a concrete barrier you see on the side of the road. Now think about what happens here. When you run up against this thing, what part of your car hits the concrete barrier first? That's right. It's the tire right here. Okay, here's your tire from the car, a little deformed, hits the barrier, and that's rubber on concrete. Let's take a look at that static friction. Wow. It's a lot higher, right? So what we found is if we can get the rubber to collide with the concrete, we're going to get a lot more friction force, which is going to help the car slow down. Another thing they found with the guardrails is sometimes, especially like in wet conditions, right, liquid or water is going to act like a lubricant. What a lubricant does is it basically fills in those microscopic hills and valleys, right? So especially in wet situations on the highway, what they found is that when cars would hit the guardrails at high speed, they basically would just careen right back into the highway. And we wanted to reduce that. And the way we do that is we increase the friction force that happens when the car hits the rail. So nowadays, you don't see guardrails, especially on any kind of new highway. You're not going to see guardrails in the middle, separating the two lanes. You're going to see these concrete barriers. And that's just using friction to maximum effect. Okay, the last thing we want to do is see how friction applies to problem solving. But before we do, I want to point out one more thing, which is that friction can be a little tricky. Friction is typically thought of as a negative thing, right? It's always working against you, but actually there are times when it can work for you. Okay, let's take the example of the car. All right, it turns out that in the case of friction and a car on a road, friction is actually in the direction of motion of the car. Now that may seem contradictory because we just defined as friction as opposing the direction of motion, right? And you're thinking, well, the car's to the right, how can the friction be to the right? Well, let's take a look at what's going on at the surface, right? If this car is moving to the right, then the wheels are rotating this way, right? So that means that actually the surface of the wheel is trying to scrape to our left, right? To our left, which means that friction will resist that intended motion and push to the right. And it's that friction force, right? And that's actually a static friction force, right? Because the tire is not scraping against, it's not scraping. That's only when you careen out of control, right? It's not scraping against the surface, so it's actually a static friction, even though the car is moving, okay? We say that the surface of the tire is instantaneously at rest with the road, okay? And so what you see is that friction is actually in the direction of motion. This is exactly how walking works as well, right? Try walking on ice and you'll see that friction is actually your friend in certain situations, right? It's the friction between you and the ground that allows you to move forward. So notice that we can retain this definition of friction in opposing the direction of motion because it's the direction of the motion of one surface relative to the other. So as the tire tries to move to the left, the friction pushes to the right, which ends up being in the direction of motion of the car. All right, finally, friction and problem solving. Let's just look at the ramp problem here. Okay, so you have the same situation. You're going to see that it's just going to basically add an extra term to your F equals ma equation, right? So if I draw the free body diagram here, that's what it looked like before, right? We had a force of weight here, okay, and force normal here. And now all you're going to get is you're going to get an extra friction term, okay, of friction acting up the ramp like that. And that means when you come over here to write F equals ma in the x and y direction, you're just going to end up with an extra term, right? So before we had mg sine theta, and now we're just going to say minus F equals ma. So there's your new term, right? It's just going to add an extra term to your equation. Now when we go down to the next line and substitute in our equation for friction, we see that we're left with this normal force term right here, right? And that's typically not going to be given to you. So what you're going to need to do is come over to the y side and write F equals ma for the y side. And that's going to look like this. It's going to be normal force minus that part of the weight. And then, of course, in the y direction, the block's not moving, right? So there's no acceleration in our y direction. And so what you get here is that n equals mg cosine theta. And that's going to be a common dynamic you see, is what, practically speaking, what friction does in terms of problem solving, the way it changes your problem solving, is that it makes you go to the y side and solve for the normal force. So then you can bring that value of the normal force in right here, right? So that our equation now is going to look like this: mg sine theta minus mu mg cosine theta equals ma, right? So now I have an equation on the left side, on the x direction, that is only one unknown, right? I can cross out the m's here. Theta is probably going to be given to me. And then I can, and mu is going to be given to me maybe, and I can solve for the acceleration, right? Or maybe they gave me the acceleration, I can solve for mu. All right, I hope you found this podcast helpful, and when we see you in class next time, we're going to apply it to some problem solving.